Hello everyone. Today I will present a technique for turning the Clang Static Analyzer slightly more incremental. My name is Balázs Benics and I work for Sonar Source. Philip Schubert and I have been working on a prototype some time now, which I will talk about today. So I will start by some motivational graphs, then I will set some context, I will recap how the engine processes a translation unit, and how inlining works. After this, I will shift focus to our prototype, walk you through what components we have and how all this fits together with the current analysis pipeline. Finally, I will close off the talk by showing some preliminary numbers of some projects, but I have to make a short disclaimer already that this is a prototype in the fairly early stages. After all this, we should have plenty of time for questions. All right. Most of you probably use static analysis tools. Hands up if you do. So yeah, I can see a lot of people are interested in this, and they are actually fantastic tools. You should use them to the greatest extent possible, but they come at some cost. They can run for ages, and one of the most time-consuming analysis technique is symbolic execution. During symbolic execution, the symbolic engine tries to explore all the paths possibly reachable and also meaningful program states in your application. It can take a while even with using some clever tricks. And if we look at some projects that we analyze, here on the graph you can see each bar representing the time spent on a given translation unit. They are sorted by the time spent on the symbolic execution phase, which is represented by the purple color here. You can also see some of the orange parts representing the time spent for parsing and producing the AST itself. There is not a lot we can do about that. The remaining red parts are irrelevant for this talk, so let's just ignore them. Luckily, or less so actually, relatively easy to spot the purple parts here on this chart, which heavily dominate everything on the rest. So that is the problem. And we can see that most translation units finish in 30 to 50 seconds at most, but the graph has this long tail, leaving the two most expensive translation units to run for more than 80 seconds here. Remember that this was only a small C project. Just imagine how this looks for larger C++ ones like LLVM or Chromium, for instance. The maximum I've seen so far was like 80 to 85 minutes on a single translation unit. So to understand why certain translation units take that long, we should have a quick recap how the engine processes a single translation unit. First, we get the AST, and then we build the call graph for that AST. After that, we select functions for analysis entry points in a reverse post-order traversal fashion by default. Once we have an entry point, we start the analysis and step by step build up a program state. If we encounter a function call of which we have the function body present, we have basically two options: either decide to inline this function or not to inline it. If we decide to inline, we map the arguments to parameters and then jump to the function body and continue as usual. Otherwise, if we chose not to inline that function, we must conservatively invalidate everything in the program state that the call could have modified. This usually means that we invalidate arguments of the call and the global variables present. Here, I have a few points to highlight. We might not inline a function, even if we technically could. Even if we inlined once a function, that doesn't necessarily mean that we will always inline it from other contexts. Once we inline the function, we consider that function covered, so we exclude it from the analysis entry point candidates. If it turns out that inlining a function was too expensive, we might back off and pretend that we didn't even try to inline it in the first place, and remember to never even try it again. All these are side effects that we need to take care about if we want to achieve an incremental analysis that preserves the behavior of the current analyzer. Let's say we finish with this entry point, But before we pick the next analysis entry point, we exclude the functions that we visited from the analysis entry point candidates, like I mentioned. Notice that there could be functions that analyze multiple times from different entry points by inlining. In this case, we only had a single shared function, but this, of course, depends heavily on the code that you analyze. We usually have plenty of entry points with only moderate sharing among them. If I will have time in the end, I will come back to this sharing principle. So, how long does it actually take to analyze a single entry point? This histogram shows us the distribution of analysis times per entry point across the whole project. Analysis times are at the bottom, and how often they occur is on the left in a logarithmic scale. We can see that a lot of entry points finish well within a second, represented by the bars at the left. Besides that, we usually only take 2 to 3 seconds to analyze an entry point, and there are not a single entry point where we waste all of our time. This graph, of course, differs from project to project, but this wavy shape remains a common theme. Now what? Couldn't we just simply fix this? It's probably not as simple as that, due to how the engine works, and in particular about inlining. It is basically unchanged since the very beginning for, 10, 15 years now. Since that, multiple companies use this product and have major changes. To have major changes in this, all these stakeholders would need to agree on a single solution. So we have what we have. Keeping major changes downstream would also bring a potential risk long term, and we also anyways just want to upstream most things that we can. Given all this, we were looking for less intrusive ways for mitigating long-term and long analysis times. Now let's have a look at our prototype. We wanted something that is minimal so that it remains simple, self-contained so that even if we can't upstream it, we can still maintain it without much additional effort. And the whole point would be to achieve some speed up for some usual cases, whatever that means. Given all these limitations, we figured we could basically just capture the diagnostics of an entry point along with its side effects, and then replay them if nothing has changed in the subsequent run. The prototype has basically 4 components. The analysis cache is for serializing and deserializing the data we might need, basically all the diagnostics in a special relocatable format, along with some hash representing the entry point, plus some other metadata, such as the side effects we recorded. The Oracle calculates the hash for the analysis entry point that we can query and compare. We use this hash to determine if we can safely replay the relocated diagnostics or not. The replayer injects the relocated diagnostics into the static analyzer pipeline. And finally, the recorder, it just captures the diagnostics of the new entry points or the ones that we decided not to replay. We also record some side effects, like how many times a given function was inlined, like I mentioned. We need these side effects to match the exact behavior of the default analysis run. Once we capture the diagnostic, we need to transform it into a relocatable format. It is something that we can save and replay later. These relocatable diagnostics must be relative to some fixed location. We call this fixed location the anchor point, or in our case, since we use decals, anchor decals. We conveniently use Clang's Unified Symbol Resolution, also known as USRs, to deterministically find these anchor points across subsequent runs. If we have to refer to an AST node somewhere under a decal, we simply use an index sequence to traverse to the right child each step, starting from that anchor point. Diagnostics are made of source ranges and the message made of a source range and a message. Usually, we don't know what AST node they correspond to, or what source location getter function produced that source location. In general, it would be difficult to map locations to AST nodes due to ambiguities. Luckily, it's not that hard to attach an AST node to the diagnostic pieces within the scope of the static analyzer. In the oracle, we want to hash the source text of the function, but we also want to make it to ignore whitespace, comment, or macro changes. Because of this, we use preprocessed source token watcher to acquire the preprocessed source text. To calculate the hash of a function, we hash the preprocessed tokens and then combine the hashes of the direct callees and also the type dependencies it has. We also follow global constants because they are also used for the Clang Static Analyzer. One entry point could have many path-sensitive diagnostics. And one path-sensitive diagnostic consists of possibly multiple steps. So we need to reanalyze an entry point if we fail to relocate even a single step of those diagnostics. Because of this, we try to relocate diagnostics early as we load them. This way, we only query the oracle if we could possibly ever replay that entry point. To complicate things, some diagnostics refer to absolute line numbers within their message. There are a few examples on the slide, and we would also need to relocate those numbers as well if we want to match the perfect behavior that the default analysis mode provides. All right, let's have a look at some preliminary numbers. Once again, a short disclaimer that this prototype is really in the early stages. Keep that in mind looking at the graphs. This approach really shines for white space or comment-only changes, in which case we basically have perfect cache hits across the board. In this small case, we basically eliminated the symbolic execution part, shaving off nearly 2 seconds. Now let's have a look at this graph, which represents 10 subsequent commits. Well, the analysis runs of those. Out of these 10 runs, only 3 changed multiple files, and you can see those 3 bars. In the rest of the commits, they only touched only a handful of files, and similarly to Ninja, we only analyzed files that were actually changed, so those bars remain barely visible. The blue bars at the top represent the default analysis time for a given commit. The orange bars represent the difference between the default run and the incremental run. If that goes into the negative scale, that means that we should save time by enabling the incremental analysis. However, if it goes to the positive side, then enabling incremental mode would cause a slowdown. If the first run should take marginally longer in incremental mode due to the extra work we do. In this case, this was actually faster, but that's of course impossible. And this tells us that the prototype didn't add much overhead so that these results remained within measurable errors for the first run. Unfortunately, this isn't always the case, and we will see it in a minute. But first, let's zoom into the last commit to see how the cache hit distributes across different translation units. On this graph, the blue bars remain to represent the default analysis time. The bars at the bottom means how much time we would spare by enabling the incremental mode. You can see that we have a significant amount of cache hits across several files, but there are still a few other ones that are less so lucky. But most importantly, there are no files which doesn't have any cache hits, which is good. Unfortunately, this prototype didn't perform too well on C++ projects, as you may see on this chart. In a lot of cases, instead of saving time, it actually takes time, which isn't good. In the future, we will definitely look into why this is the case, and I will also speculate on the next slide. Now, Let's zoom in to the last translation unit, like we did last time. We can see that for we can see that for some translation units, we don't have any cache hits at all, which is the unexpected behavior I was referring to. I could speculate, of course, and my guess would be that the type dependencies, especially for C++, can get fairly wide and deep, causing these cache misses. We could probably refine and relax the dependency collection to accommodate for this. We will see how this goes in the future. This approach keeps one weakness of the underlying engine. Consider the case when all entry points inline roughly the same set of functions. I call this sharing, as those functions are shared across these entry points. So if any of those change, all entry points might have changed. We knew about this poisoning effect, and we measured how much sharing we usually have in practice. And it seems like I have time to go into details there, so let's have a look. There's a lot of things to unpack here, but on this compound graph, we correlate the translation running times and the sharing. We have two graphs, one at the top and one at the bottom. First, look at the bottom chart. At the bottom, we have analysis times per translation unit. They are not sorted in any particular order. At the top, we have the analysis time per entry point, so each dot represents that. You can read how long it took on the left side of that chart for that particular entry point, and that's why we have multiple points on a single column. Basically, the higher the dot is, the longer it took to run. The size of the dots are not relevant for this talk, but the color is. If it's green, then the entry point usually only refers to a handful of functions, so that sharing is not prevalent there. But if it's red, then it means many functions are shared across multiple entry points. Basically, many red dots in a single line means significant sharing, and the prototype wouldn't be effective. And you can see that actually the more red dots you have in a column, the more running time it usually leads to. This is without the prototype. This is inherently from the analysis engine, how it behaves. And unfortunately, we can't really help with that. But this also seems that it's not too frequent enough, so this prototype seems still relevant, even after this. To conclude, so far we have only had moderate improvements overall. We need to investigate a couple more cases and improve on, especially for C++. There is still a lot of potential left in this technique, I believe. I've seen many cases of trivial changes like whitespace, comment, or narrow local changes where this technique worked really well. And I think incremental mode would be especially useful for pull requests and analysis within your IDE. And now we have plenty of time for questions if you have.
All right, well, we're waiting for any question. I have one about the inlining. Is the inlining strategy different from what a compiler would do for optimization for the static analysis?
So I can't really speak for how the compiler actually optimizes things, because it's outside of my expertise. But yes, some heuristics take into account how large the callee function is, where is that, for instance, if it's within a system header or not, and how many times it was in the past inlined, and stuff like that. So and we also have that if it turns out it was expensive once, then we will remember that to never inline it again. So yeah, stuff like that, a bunch of heuristics like that.
All right, and then another question about, so you they're clearly time improvement, but what is the memory cost of all the caching? Is it negligible, a few megabytes here, or can it be big if you have a big project?
Oh yes. So while we developed this, we had some challenges. We ran out of memory a couple of times, but we managed to push it back down. So it tops at around at most 1 gigabyte I've seen, but that wasn't really in the primary focus so far. Yeah. So yeah, and speaking of the storage cost for storing these incremental stuff, that we in particular didn't measure, but it's highly well compressible. So we could just simply compress it and store it like that.
Interesting. Thank you very much, Balázs. Well, if there's no other questions, we'll just take a little bit longer recess. So next session starts at 11. And if the next panel speakers are here, if they can make sure that they get a mic at the technical spot here. Well, thank you very much.